Thank you for joining in, and I hope all of you are doing well. I am Aditya Dubey. I'm a PhD student at RMIT University, and today I'm going to give a presentation about my work, which involves fabrication of nonlinear photonic integrated circuits for second harmonic generation. Second harmonic generation is a process in which two photons combine within a nonlinear material to generate another photon, twice the frequency or half the wavelength. So for instance, when you apply a strong electric field, such as from a laser to a nonlinear crystal, it results in the generation of a second harmonic wave with half the wavelength of its initial power. And a very good example of such nonlinear frequency conversion is a green laser pointer, which works on the same principle with a high intensity laser source, which is an IR diode, and a nonlinear crystal, typically KTP crystal, which allows this nonlinear frequency conversion from infrared to visible, giving such green emission. Now, why is this even important? Now, the primary advantage of such nonlinear frequency conversion is that it allows accessing wavelengths where it's difficult to have high quality laser diode. But its applications are not only limited to that. It also finds its prevalence in a wide range of applications in diverse fields, from biological imaging to optical communication, in sensing, in quantum optic experiments with photon pair generation, and many more. But particularly when we talk about photonic integrated circuits, as we know over the years, there's been extensive research focused on downsizing these bulk scale optical systems into chip level integrated circuits to improve its functional performance by reducing size, cost, and power consumption. And this trend has given rise to the introduction of a number of platforms based on materials such as silicon on insulators, silicon nitride, 3,5 compound, each tailored for the specific applications. Likewise, lithium niobate on insulator is relatively new, but an emerging platform which really stands out due to its strong electro-optic and nonlinear properties. And due to these characteristics, including few more mentioned here, there's been demonstration of high performance modulators, optical frequency comms, low loss waveguides, and many more. But particularly for second harmonic generation, it really distinguishes itself from its counterparts due to its strong nonlinear properties, thereby making it an ideal candidate for second harmonic based demonstration. However, even with that, there is still a fundamental issue with second harmonic generation which limits its conversion efficiency. And that is the inherent phase mismatch between the fundamental and the generated second harmonic wave as they travel within this nonlinear crystal. Due to their difference in speed, this is the dispersion. And where ideally you would expect the conversion efficiency to grow exponentially with length, but due to this dispersion or due to this inherent phase mismatch, the conversion efficiency diminishes over length. And this is a big issue. And to overcome this, a method known as quasi-phase matching is introduced, where the polarization of the crystal is periodically inverted to maintain a phase matching condition between both the waves, thereby enabling a gradual increase in conversion efficiency over length. And the technique to achieve this periodic domain inversion is called periodic polling. Now, how this is even possible in lithium niobate? For reference, here is a crystal structure of its unit cell. And interestingly, it exhibits ferroelectric properties, which means with domain inversion is possible with the displacement of this lithium and niobium ions from the initial position. But to be able to do that, a huge amount of field is required to really push these ions from the initial position. Here, a dominant method known as electric field polling is used, where high voltage pulses in the range of hundreds of volts are applied to these comb-shaped electrodes to achieve this localized domain inversion, where the domains nucleate from the tip of the positive electrodes and terminates towards the other end of the electrode. And this periodic domain inversion is what is essential for quasi-phase matching and thereby efficient conversion efficiency for second harmonic generation. Now, here is a fabrication flow of how this can be really fabricated, which starts with the patterning of the electrodes. And this is done through tools such as laser lithography or electron beam lithography. After the patterning material, the electrode material is deposited using tools such as e-beam evaporation. And after the electrodes have been deposited, these are then applied with a series of high voltage pulses through the same method as discussed in the previous slide, the electric field polling. And the electrodes are then applied with a series of high voltage pulses to achieve this uniformly poled domains or domain inversion. Once the polling yield is confirmed or is desirable, the electrodes are then etched away and a waveguide is patterned to sit within these uniformly poled domains, where the light could be coupled in from one end, the fundamental beam, and a second harmonic signal can be detected towards the other end, the half the wavelength of the initial pump. Now, here it is interesting to note that the conversion efficiency of these devices primarily depends upon how good these domains are uniformly distributed across the length of the crystal or the waveguide. And this is the major issue with the fabrication of these devices, as it is very difficult to have a really good control over the domain dimensions due to their semi-random domain nucleation tendencies. So where ideally one expects to have a duty cycle closer to 50% with uniformly poled domains, but prevalent issues such as overpoling, underpoling, or semi-random domain nucleation or growth process really affects it. So these non-uniformities in the domain evolution process limit the conversion efficiency of these devices, especially the longer periodically poled devices, where otherwise the conversion efficiency is expected to grow exponentially with length. And this also forms the motivation behind my work, where I work towards optimizing the periodic polling in a 300 nanometer thin film lithium niobate on insulator platform to achieve uniform pole domains to have enhanced nonlinear frequency conversion in this platform. Now, another interesting thing to note here is that these uniformly or these domain inverted domains cannot be seen through a standard optical microscope, hence sophisticated visualization methods are needed. So in my work, I've opted two approaches. The first is a destructive approach, which uses a selective chemical etching of lithium niobate thin film cross-section. And it is a very common method which is used, and it uses the fact that opposite phases of the lithium niobate etches at different rate in an HF solution, thereby making them easily distinguishable after etching has been done. So here are some examples of SEM images with underpoled, overpoled, and uniformly poled domains, which is desired in our case. Now, overall, this approach provides really decent insight into the domain shape and size, but also in-depth nucleation. However, to make the fabrication much easier, flexible, or dynamic, I've also tested another approach, which is second harmonic confocal imaging. So in this process, a fundamental beam in the infrared range is tightly focused on a lithium niobate crystal, and due to the nonlinearity, it results in the generation of a second harmonic signal, which is then collected in the backward direction. And the scanning of the surface area of the sample gives a resultant image such as shown here, where the dark regions can be interpreted as the electrodes, and from the tip of the positive electrodes you can see this visible domain nucleation. And that is clearly not visible in the standard optical microscope image of the same sample surface area. Now, it is also interesting to note that each one of these domains slightly look different in shape and size than the other, even though the pulse applied to them is exactly the same. So this is the reason why there's a need to optimize the polling supply or the polling process to achieve uniformly poled domains for enhanced quasi-phase matching and thereby enhanced nonlinear frequency conversion. So with that, with both the visualization approach, we did successive iteration and tested with different polling parameters such as polling voltage, pulse duration, number of cycles, electrode shapes and size and material. And with that, here are some examples of silicon nitride loaded waveguide that is fabricated to sit within these optimized uniformly poled domains. And this is from a very recent fabrication run where the silicon nitride, after the polling electrodes have been etched away, the silicon nitride is deposited using plasma enhanced chemical vapor deposition, followed by the waveguide formation through electron beam lithography and reactive ion etching. Now, unfortunately, at the moment, these devices are still being characterized, but after the characterization is finished, it will give us some insights on how good the second harmonic response is through this device and how it compares with already reported demonstration in a similar platform with similar length of waveguide. And with that, I will take my work further in producing or optimizing the fabrication process and producing longer periodically poled waveguides with enhanced nonlinear frequency conversion, and then later demonstrate these devices with integration for applications in data communication and quantum realm. And here one example for data communication would be using this device for wavelength band conversion to utilize the unoccupied wavelength band for transmission, and thereby enhancing the data capacity of network system. Now, at last, with that, I would like to finally acknowledge the MCN node of ANFF, where I conducted most of my work involving silicon nitride deposition and silicon nitride waveguide formation. I would also like to acknowledge the MNRF facility at RMIT University in the staff, where I conducted most of my experiments with the optimization of periodic polling and different visualization approaches. And that is all. Thank you. Please feel free to ask any questions if you have.
Thank you, Aditya. Any questions in the room? Oh, yes.
So a quick question on your second harmonic characterization. Is that a system that you built yourself, or is that something you can sort of get off the shelf, or somebody else can put together?
This is from out of the shelf. This is a system that's been supplied to us in one of the lab from Olympus. So it's a scanning electron microscope multiphoton imaging tool, which I've used with appropriate filters to filter out the second harmonic response. But yes, it's not been built from the scratch, but it's already been deployed to us through an industry.
Anybody else? Okay, well, thank you very much, Aditya.
Thank you.